quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Hello everybody, and welcome to episode number 14 of Patterson in Pursuit. It seems like these interviews just keep getting better and better and more exciting. This interview I am the most excited about because, in my own intellectual pursuit, I have come across several areas of thought that people draw from when they try to make what I call irrational conclusions. They try to say, oh, reality is logically contradictory, we can't know anything about anything, and the universe is a great blurry paradox, or consciousness is at the center of the entire universe. These ideas, I think, are foundationally inaccurate, dangerous, and are about as far away from rational, clear-headed thinking as possible. And quantum physics is arguably the area that gets the most citations from the irrationalists. An extraordinary amount of words have been written, drawing from the supposed conclusions of quantum physics to show how irrational the world actually is. But in my own research, when I actually dove into the field, I found a lot of these conclusions to be mistaken. I think people who draw from quantum physics to make radical conclusions don't actually understand what they're talking about. They make grave errors with very big implications. So what I did explicitly while in England was set up an interview at the University of Oxford with a professor of the philosophy of physics to try to get down and pin down the core concepts in quantum physics for everybody to understand. And this interview is with Dr. Simon Saunders, who is indeed this professor I was looking for. Dr. Saunders is a professor of the philosophy of physics at Oxford University. He's written a ton of papers on the topic, he's written a few books, and what I find of inestimable value is that Dr. Saunders focuses on concepts. Very often when you have elite intellectuals who are nose deep in their own research, they get mired up in a lot of jargon, a lot of mathematics, a lot of specifics that nobody outside their own field understands. And in this interview, we only talk about mathematics really in the abstract. We just focus on the concepts, which I think is necessary if you want to clearly understand whatever field you're talking about. You have to be able to understand it clear enough where you can break down the basic concepts. That's not to say, however, that this is an easy interview or this is something that you'll be able to sit down and, halfway ignore and still be able to follow along, especially if you have no background in physics whatsoever. So what I've done to help make it a bit easier is for about the first 15 minutes or so, I'm going to be chiming in to give additional clarity to the interview as it's taking place. So maybe 5 or so times I'm going to jump in and try to break things down to have that much more clarity. So before I start this interview, I want to give a gigantic shout out to all of my Patreon supporters, especially the ones who support my work the most. Thank you very much, Mark Gouvet, Charlie Davis, Melvin Martinez, Sean Baleda, John LeBlanc, the Georgia Freeman, Michael Sedlak, David Richardson, Samuel Robert, and David Baumberger. Thank you all very much for supporting the creation of a rational worldview, and everybody else that is supporting at smaller levels. Your support makes these interviews possible. All right, that's enough for me. I hope you really enjoy my interview with Dr. Simon Saunders. So first of all, thank you very much for talking with me today.
It's a pleasure.
I have asked a great deal of you because, as you know, in the world of philosophy and the general public, quantum physics gets thrown about all the time. People try to justify all kinds of remarkable propositions when they're talking about quantum physics.
Indeed.
What I've asked is if we could slowly work through the basic concepts so when people are trying to evaluate the plausibility of some of these ideas, they'll have kind of the conceptual toolbox that they need.
Right.
So correct me if I'm wrong at any point in this, that one of the peculiarities in the world of quantum physics. Kind of the first experiment, or the foundational experiment, is called the double slit experiment. That's kind of where we see this remarkable phenomena that people make all kinds of incredible claims. You can analyze quantum physics by analyzing the double slit experiment. And what that is we have 3 parts in our experiment. We have a light source, we have like a plate that we're going to be shining the light at, and then we have a screen. Okay, so this is the first time I want to jump in, because when talking about quantum mechanics, you must understand fully the setup of the double slit experiment. Really, the double slit experiment is central. That's really the whole, everything really follows from the phenomena that you can observe with the double slit experiment. So in this example, when I'm talking with the professor, we're talking about light, because that's the actual setup that physicists use when they're performing the double slit experiment. But conceptually, you can also think of it another, perhaps even more intuitive way. Instead of light, let's talk about sand. So imagine you have a setup of 3 parts. On the top, you have a hopper that's full of sand. And the sand is slowly dripping down onto the second part of the experiment, which is, let's call it a card. On the card, there are 2 slits in the card that allow the sand to pass through those slits. Below the card, we have a screen where we can see the resulting pattern that happens once the sand goes from the hopper through the slits down onto the ground. So sometimes we can plug one of the slits to record what happens as the sand passes through the one slit. We can have both the slits open and record the pattern that happens. So conceptually, that's what the double slit experiment is. You have 3 parts. You have the reservoir of particles that are being shot at a card, or I call it a plate with 2 slits in it, and then you have the screen behind it to record the pattern that results as those particles go through the slits. And in that plate that we're shining the light at, we have, let's just say, 1 slit. Now, if we do that and we shine the light at the plate and see what happens, if we're seeing what happens to the pattern on the wall, we're just going to have a blob of light on the wall, regular light. But when we open up a slit next to that first slit, what we would intuitively think is you'd see 2 blobs of light, or a different diffraction pattern. But what you see is what appears to be wave interference, where you have some bands of light are bright, and then it goes dark, and then it goes bright, and it goes dark, which is very peculiar, because I think we intuitively think, correct me if I'm wrong, that in physics you have waves and you have particles, and these things aren't really together. They're kind of 2 mutually exclusive things. But just in that experiment, it seems like you have waveness and particleness at the same time. Is that fair so far?
Yeah, absolutely, although you haven't indicated why we think we have particles present. We have a light source, suppose it's of moderate intensity, the sort of thing you'd get from a flashlight. Of course, we see a blob. You have the 2 slits open. We see what we call interference fringes. But there's nothing strange about that. All of that is wave theory of light. What's strange is when you reduce the intensity of the light source to the point where we start to see not a very, very, very faint blob or very, very, very faint fringes, but we see 1 speck at a time. The interference fringes are built up out of innumerable individual events, each of which looks like a particle is impacted on the screen.
So let's say this even more clearly. So if you reduce, instead of just 1 stream of light, let's say you do 1 little particle of light at a time.
You've got to reduce the intensity enormously.
Right. What happens is you still have what appears to be the wave interference. And the question is, well, how's that possible? Because it's just 1 bit at a time.
Right. It's 1 particle at a time, absolutely.
Okay, so then it gets even weirder. If we were to ask the question, when we shoot that 1 particle at a time at the 2 slits, the sensible question is to ask, which slit is the particle going to go through, the one on the right or the one on the left? Well, when we try to measure that, which one, we put some detector there to see which slit it goes through, the wave pattern disappears.
Right.
Now you can measure, it'll go through the one on the right and the one on the left, but you won't have the wave pattern.
Right.
But when you turn that measurement off, so you don't know which one it goes through, boom, the wave pattern reappears.
Right, exactly. Crazy. Yeah.
So this is a fair restatement.
Absolutely.
Okay, so I want to state that again just so it's absolutely crystal clear. When we fire the particle at the slit, we don't know beforehand whether or not the particle is going to go through the slit on the right or the particle is going to go through the slit on the left. So naturally, a sensible question is to ask, let's find out. So what physicists do is they set up an apparatus which measures which slit the particle goes through. However, when they do that, when they actively measure and find out which slit the particle goes through, the interference pattern disappears on the screen behind them. And similarly, when they aren't measuring which slit the particle goes through, the interference pattern, it reemerges. And this is precisely what has caused so much confusion, is the peculiarity of this phenomenon. So let's try to then break this apart and say, what the heck is going on here? Because intuitively, it seems like there's some funny business. There are different competing interpretations for explaining what that phenomena is. How is this possible?
Right.
One that would be the most intuitive, just to anybody who's listening, would be, oh, well, what's happening is, at least when we're talking about measuring or seeing which hole the particle goes through, whatever equipment that you're measuring that with, that's got to interfere with the experiment somehow, because it's interfering with wave pattern.
Right.
What is that?
Yep, no, that's a perfectly appropriate response to this straightforward fact. Determine which slit the particle goes through, no interference pattern, indeed. And we think that whatever the detection device is that's interacting with particles as they go through one or other of the slits, or as they approach the two slits at any rate, that interaction, it's a physical effect and it destroys the interference pattern.
So that is uncontroversial, you would say, that
Right.
there's some kind of... Okay.
Right.
So the standard theory in quantum physics for the last nearly a century now
Right.
has been the Copenhagen interpretation of quantum physics. So,
right, I mean, I have some caveat about that, but go ahead.
okay, and from my understanding, that's a little bit less popular than it is now, but it's still kind of the standard textbook theory that's taught.
Well, again, I have a caveat.
Okay,
Do
what
you
was
want
the
me to
caveat?
say that?
Yes,
okay.
of course.
So the caveat is this. Copenhagen was a coin termed by Werner Heisenberg in the post-Second World War period to talk specifically about Bohr's interpretation of quantum mechanics. Bohr was based in Copenhagen. So if that's what the word means, Copenhagen interpretation means Bohr's interpretation, that interpretation was influential. It was studied by physicists in the late 20s and 30s. It's hardly ever been studied since.
Really?
Right.
And now so that's not the one that's being taught in terms of...
It's certainly not taught.
Okay.
You won't find it in almost no textbook, contemporary textbook published in the last 30, 40 years. Some no doubt will have Copenhagen somewhere occurring in the text, but most of them, the vast majority, don't mention the Copenhagen interpretation per se, do not mention Bohr's interpretation per se. So what the Copenhagen interpretation can get to mean these days is a kind of a minimal interpretation, which is in most textbooks on quantum mechanics and takes the form of the measurement postulates.
Okay.
So standard quantum mechanics comes with these measurement postulates. Physicists mostly just get on with the job, shut up and calculate. Philosophers and people concerned with foundations of quantum mechanics are extremely troubled by the measurement postulates.
Okay.
And the reasons for that are interesting. I could go into them if you wish.
Yes, so let's talk a little bit about what you mean by the measurement.
So what are the measurement postulates? Yeah. Okay. So what we have in quantum mechanics is a state space common to most other theories of physics, a space indicating the possible states that a system can be in. We have a dynamical evolution defined on that state space, which goes by the name of the unitary evolution in quantum mechanics, because the relevant transformation has mathematical characteristics of a transformation called unitary. But it's a very specific unitary transformation. It involves all of the details of the dynamical interactions. These details are what physicists work on in high-energy particle physics, for example. We have the so-called standard model. The standard model is all about the nature of that dynamical evolution of the state. And you can win Nobel Prizes for coming up with new dynamical evolutions for the state. There are lots and lots of empirical tests for determining whether a given dynamical evolution is correct. So this is, as it were, the mainstay of physical research in foundations of quantum. Let me not say foundations of quantum theory. This is physical research in threshold physics. Let's call it that. We're trying to get down to Planck scale physics. In a sense, this is physics as normal.
Okay, so that's a very technical way of just saying that physicists like to very tightly control the environment and the setup of their experiments. So when he's talking about state spaces and stuff, just think of it as physicists are trying to precisely identify and control phenomena that happens in particular spaces. And when he's talking about unitary evolution, just think about accurately recording the phenomena that's taking place in that space. And the so-called standard model of physics has to do with macroscopic phenomena, large-scale phenomena. So, the bowling ball rolling down the lane, that's something that the world of standard physics has sorted out to an incredible degree. And as we get smaller and smaller and smaller scale, so it's not macroscopic, it goes microscopic and then, super microscopic, it appears as if the laws of physics are different. So the beauty and the simplicity and the predictive power of standard physics when we're talking about the bowling ball is very precise. However, the smaller scale we go down to this quantum scale, the microscopic scale, the less precise and more difficult things are.
Okay, so go back to the measurement postulates. We have the state space, we have this unitary evolution, which physicists are preoccupied with, to get the details of that unitary evolution right. But then we have the measurement postulates in addition to that. And what the measurement postulates direct us to do is to interpret the state of the system in terms of a probability assignment. Mm-hmm. And the probability assignment is about outcomes of measurement. Depending on what sort of measurement is performed, the measurement postulate will tell you how to compute a probability for that outcome.
Mm-hmm. Okay, so this is a very central idea that comes up in quantum mechanics, so we're going to be talking about it throughout the interview. But it has to do with the imprecision of our measurements when we're dealing with quantum scale phenomena. So in contrast to the circumstance, the macroscopic phenomena of the bowling ball going down the lane, where we can have perfect precision. So if you know all of the inputs and variables going into the experiment, let's say with rolling the bowling ball down the lane, you're going to know a perfect precise outcome. Well, in the world of quantum physics, that's not the case. You can know the inputs, but you don't necessarily know the outputs. So when physicists come up with a model to explain this, they aren't dealing with perfect precision. They're dealing with probability functions. They aren't saying, for example, if you start the race here and you're moving with this certain velocity, you'll end the race here. They're saying if you start the race here, then we have a relative probability function of where you're going to end up. We can't be certain exactly where that is.
Now, that may or may not strike you as peculiar. What's peculiar, and I think this is probably the core of the matter. It's taken a long time to really refine this down to this, but I think it is the core of the matter, is that this postulate, it depends on the kind of measurement we wish to make. This is not got the character of a physical law. Okay. It's, one way of putting it is it's too high level. What kind of experiment we're making involves intentionality, it involves questions of the design of an experiment. It seems to refer to actions taken by experimenters. We know of no other physical theory in which facts of that sort are factored into the fundamental laws.
So in other words, what you're saying is there's this essential connection between the setup of the experiment, the experimenters, and the results of the experiment.
Right. One would hope to make progress in getting rid of this measurement postulate referring to high-level intentionality and so forth of what an experiment is supposed to do. By just describing the measurement apparatus as a physical system, just making that a part of the explicit dynamics to be dictated by this unitary evolution. Right. But when we do that, what we get out, the quantum state at the end of this dynamical interaction involving the measurement interaction, what we get out, the dynamical state that we get out, has, it seems, no meaningful interpretation.
Okay, so what that means is when we're dealing with these extremely small-scale phenomena, the actual tools of measurement are essentially part of the experiment, Because the only way to record particular states of a system are to physically interact with that system, the physical interaction of measurement affects the whole experiment itself. It's an essential part. Imagine that you're trying to take the temperature of a glass of water that you have in front of you. Well, you could do that by placing a thermometer in the water. However, just the simple act of placing the thermometer in the water is going to affect the water temperature itself. There's no way to perfectly, pristinely know what the temperature of that water is without interacting with it in such a way. And usually when we're talking about macroscopic phenomena, large-scale phenomena, the impact of the measurement is negligible. It doesn't really make a difference. However, when you're talking about micro scale phenomena, the actual measurement does make a difference, and in fact appears to be a central part of the results that you get is this act of measurement. And what he's saying is this goes very deep. So it goes from the setup of the experiment to the tools of the experiment to the humans that are setting up the experiment to the intentions of the humans that are setting up the experiment. You get this very unsatisfactory circular spiral in which just interjecting measurement into the equation, the phenomena of measurement, is going to essentially change the results.
The way to make it meaningful is, again, to apply the measurement postulates. So we're back to square one. In other words, it just doesn't succeed. You try to put the content of the measurement postulate into a physical characterization of an experimental device, run the dynamics, you haven't got out a meaningful prediction. To get a meaningful prediction out of this enlarged system, now we've included the experimental apparatus, we have yet again to apply the measurement postulates. So the straightforward moves don't work. And that really is the measurement postulate. Granted that the straightforward moves don't work, what do you do about it?
Okay.
Right.
So let's try to take a metaphysical example of what we're talking about here to give it some concreteness. Let's talk about a famous example, Schrodinger's cat, where imagine that there's a cat in a box. And inside of the box, there's also, let's say, a flask, that if the flask breaks, then the cat will die. If the flask doesn't break, then the cat lives. And what determines whether or not that flask breaks is some kind of quantum event that we can't necessarily predict beforehand whether it will or it won't happen, but we have a probability function. We say, well, 50% of the time it will break, 50% of the time it won't. Now, when you're talking about this interpretation of quantum physics, what does it say about the state of the cat? Is the state of the cat both alive and dead? Is it neither? Is it only when you look at the box, does then it take a state? What is the position?
Sure. Taking the cat and the radioactive decay detector and so forth, the whole contraption, this is exactly a case of a macroscopic measurement device. You might say this is what the measurement postulates involve. Now we've got the measurement device as this complex system involving a living cat. Do the dynamics. The dynamical evolution will take you to a quantum state which, as per what I was previously saying, has no physical interpretation, or not in the first instance anyway. What do? Well, we can apply the measurement postulates. When we apply the measurement postulates, then we'll get outcome cat dead with some probability, cat alive with some probability, fine. But we have had to apply the measurement postulates from the outside. We can't, for example, regard the cat as itself in the position of an observer.
Okay, so the next central concept to understand has to do with terminology, and this is where a lot of people get tripped up. This is where you get a lot of really crazy ideas that coming from quantum physics. It has to do with terminology about measurement and observation. Now, in common parlance, we think of terms like observation or measurement having to do something with awareness, like human awareness of some phenomena. Well, that isn't the case. We talk a lot more about this later on in the interview, but observation or measurement in regards to physics, you have to think of it as physical interaction with a measurement device. That is observation. So for example, with the cup of water, the thermometer being placed in the water is the observation. It is the measurement. It has nothing to do with human awareness.
the cat, as it were, cannot apply the measurement postulates. The measurement postulates seem to have to make essential reference, in this case, to something over and beyond the cat and the contraption that it's connected to.
So essentially what you're saying, I think, is that in this particular interpretation,
It's not an interpretation as yet. This is just standard quantum mechanics.
Well, that's kind of what the interpretation is that there is no interpretation, right?
Okay, great, right.
Yeah,
fine,
So the central idea in standard quantum mechanics is this, that there is no meaningful unobserved state out there that we can really even talk about.
Well, when I said try to get rid of the measurement postulates by putting the physical apparatus into the physical description and just coupling it dynamically to the system under observation and just turn the handle, evolve the dynamics, we end up with something, a quantum state that has no meaningful interpretation. One way of describing that state is as the state in which the cat is in a superposition of being alive and dead.
Okay, so let's talk about that.
And generically, can I say, whenever you do a macroscopic experiment, if you just rely on the unitary dynamics, what you will get out is a superposition of all of the possible outcomes of the experiment. So the cat is just a vivid way of illustrating that and how peculiar that is. It's also peculiar, I mean, it's peculiar for a cat to be in a superposition of being alive or dead. It's also peculiar for a measurement outcome to be in the superposition of one outcome and another outcome.
So let's explore that concept of the superposition, because intuitively that seems like, well, that's nonsense. I mean, you can't have a cat that's alive and dead at the same time. And a lot of people, this concept, people have applied to justify the existence of logical contradictions. They say things like, oh, we know classical logic doesn't apply to the world because quantum physics shows that you have cats that are alive at the same time. What is your response to that?
Right. Well, the idea that some revised logic is necessary to interpret quantum theory, it was attractive. It was first floated in the 60s by people like David Finkelstein, taken up by Hilary Putnam. It fitted with a view of the revolution brought by general relativity, where geometry that was thought to be a priori and well understood. We have a Euclidean geometry. This is fundamental to science, fundamental to mathematics, fundamental to our understanding of the world. Lo and behold, we've had to revise it in the light of general relativity. And parallel logic, a priori, was thought to be a priori, is involved in our dealings with the world, is fundamental to science. Guess what? We have to revise that too. There was a fairly attractive parallelism, really, between the two developments. But the long and the short of it is, when it comes to revising logic, you can sort of do it, but it doesn't help. It doesn't actually resolve the conceptual problems. So nowadays, I think almost no one looks to a revision of logic as a solution to the measurement problem of quantum mechanics. What we've been talking about is called that, the measurement problem of quantum mechanics.
Right. Perhaps no one in the profession believes that, because there's certainly lots of people outside the profession who think that this does indeed show the problems, the limitations, the non-applicability, really, of classical logic. So let's try to take this, if we can, from Schrodinger's cat back to the double-slit experiment. So where does the concept of superposition fit into the double-slit experiment? Could you say something like the particle goes through the slit on the left and the right at the same time? Does that work?
Let's be more accurate. The particle is in a superposition of passing through the left-hand slit and the right-hand slit.
So what does that mean?
Right. Okay. So we're back to the fundamental question of what do superpositions, what do they mean?
Yes.
Okay. So there are essentially three ways of making sense of this.
Okay.
Okay, let me go through the more intuitively, the less challenging of them.
Okay.
So the less intuitively challenging. So I think of all of the three, the straightforward idea is we need to add something more to the quantum formalism. The quantum formalism with this dynamical evolution of the state is not the whole story. What is also needed are further variables describing the actual particle motion. The quantum state on its own is not enough.
I see.
So such variables are called hidden variables. Whether that's good terminology or not, let's not worry about it. Some people complain about the terminology. They are additional variables, and they describe the trajectories of actual particles. And these are point particles. Okay, so structureless point particles are supposed to have definite trajectories. These hidden or additional variables describe those trajectories. Such a particle either goes through the left-hand slit or it goes through the right-hand slit. It never goes through both slits. It eventually arrives at the screen. That explains how come we see the image at the screen built up one little pixel at a time, one little point at a time. And now the peculiarity of the two-slit experiment is explained because there is in addition the quantum state, and the quantum state propagates as a wave through both slits, and that quantum state influences or guides, as it's often called, the trajectory of the particle, this point particle. This guidance goes, there's a mathematical equation corresponding to that called the guidance equation, and actually there's no longer any problem with the two-slit experiment according to this approach.
And this would be called something like the pilot wave theory, right?
Indeed, the best developed, indeed the only developed theory of this kind, which adds these additional variables, is called the pilot wave theory, also called the de Broglie-Bohm theory, after Louis de Broglie in the 20s, who first proposed it, and David Bohm in the 50s, who independently came up with it. And for reasons that aren't entirely straightforward, it's often also called Bohmian mechanics. These are people who really have neglected de Broglie's contribution. And so-called Bohmians really became a significant movement in foundations of physics, a significant school of thought, really in the late 70s, 80s, partly under the influence of the work of John Bell. But certainly in the East Coast there are various communities of so-called Bohmian people who promote this.
And that's different from Bohemian.
It is indeed. who promote this approach to quantum theory. Right. Okay, so that's one school, and you might well.
May I just interrupt you just here? So to be clear, as it relates to superposition, this pilot wave interpretation says it's not actually a position. That superposition.
No, there is a superposition, but it's a superposition. It's a superposition of the quantum state. Just think of a wave. We have superpositions of waves, superpositions of water waves. You generate a water wave in your corner of the swimming pool. If I break my hand up and down in my corner of the swimming pool, we can see those waves propagating towards one another, and there's some interference among those waves. We're very, very familiar with this. We see the same phenomena in acoustics with sound waves and interference. We see it with radio waves. We see it with light waves, thinking of them as waves. There's no mystery with a waveform being a superposition. The mystery, or the straight-out apparent contradiction, is when you talk about a particle position being a superposition.
Right. I see what you're saying.
On the pilot wave, the particle always has a definite trajectory.
I see. Okay, my mistake then in thinking about this was equating superposition with particle superposition, and we're talking about wave superposition. Got it. Okay.
In the pilot wave interpretation, the thing is solved in that way. Okay. So now. Another approach, the dynamical collapse approach, it doesn't add new variables to the quantum equations of motion. It changes those equations of motion. And it changes them by building in really what is a fragment of the measurement postulate. That fragment is mathematically defined. Let me not try to articulate it in speech. But so this modified dynamics, so long as the particle is, roughly speaking, not interacting with other particles, so long as it's freely propagating through something like a vacuum, what we have is a wave. Now that wave goes through both slits, and it produces interference effects with one another. But that wave, on interacting with the screen, is subject to a dynamical process explicitly controlled by the equations, which leads to the wave becoming localized at one point in the screen rather than some other point in the screen. So this is rather remarkable. It's not easy to understand how the wave achieves this remarkable process of localization other than by going to the mathematics. But the mathematics is well defined. That's what the quantum state does when driven by this modified dynamics.
And what is this called? What is this theory called?
A dynamical collapse theory.
Okay.
And the best worked out version of it is the GRW or GRWP theory after Gerardi, Rimini and Weber.
Is this fairly new?
And Philip Pearl. Okay, so this GRWP theory GRW first emerged in the late 80s.
I see.
And by the early 90s we had a fairly worked out and satisfactory such theory in the non-relativistic regime.
Okay, and we'll get to that maybe a little bit later.
Right, let's get to that later.
Okay.
Sure. So that's the second way of making sense of this phenomena. And in this, under this dynamical collapse theory, you don't need any measurement postulates. You just have the dynamical equation, right? Okay, so the third way of making sense of the theory is actually to leave the theory as it is. Don't introduce additional variables. Don't modify the dynamics. Just take the existing dynamics, the standard dynamics, the kind of dynamics that physicists routinely work on at threshold physics, frontiers of physics. Take that dynamics, apply it to complex systems. Apply it to individual particles, sure, but equally apply it to the two slits, apply it to the screen, apply it to the Schrödinger cat, apply it to whatever experimenters or observers there are in addition to Schrödinger's cat, in addition to the screen, the two slits and the source. In other words, apply it ultimately to the universe as a whole. Mm-hmm. Okay, now when you do that, you get the extraordinary and apparently uninterpretable result that you've got a superposition of the cat alive and dead, that you've got a superposition of the particle arriving at one point of the screen and at another point of the screen, and guess what, because now we put the observer into the picture as well, you've got a superposition of observers seeing the cat alive, and observers seeing the cat dead.
Right.
Okay. Now, because we're just allowing quantum mechanics to apply to the whole universe, ultimately, what you finally end up with is a superposition of two different universes, the one in which the cat lives, the other in which the cat dies.
I see.
Right. So this is called the many worlds interpretation, also called the Everett interpretation, because the first person to come up with it was a physicist called Hugh Everett in the late 50s. And of the three, it's the only one that leaves quantum mechanics unchanged. That's the fundamental point in its favour.
So with that one, with the Everett interpretation and the many worlds interpretation, doesn't that imply then you have a very, very, very large amount of different universes?
Oh, absolutely.
that are constantly splitting off.
Absolutely. Yes. And this is viewed as a priori unacceptable by many. Okay, whether it's appropriate to have a priori judgments about fundamental physics is another question, which I'm very happy to discuss. But for many people, this just rules it out as unacceptable.
Okay.
So for those who are prepared to grant that the universe may be much, much, much stranger than we think it is, the fact that we have virtually an infinite number of parallel universes is not easy to get used to. But put into the picture what cosmology teaches us, because cosmology also, by the lights of many, is completely unreasonable, and one might have a priori reasons to think that the universe can't possibly be as cosmologists tell us it is. Cosmologists tell us that it is large to a number which it defies imagination, and it may indeed be infinite. Okay, so physics is not easy. And I don't here refer so much to the technical difficulties. I refer to the challenge that it presents to common sense.
Right. So let me ask you a question. If this is a fair way to categorize the distinction between what I was calling Copenhagen, which maybe I need a different term for, and the many worlds.
Right.
So when we're talking about superposition, Copenhagen implies that in the same universe you have two what appear to be mutually exclusive states.
Right.
Whereas in the many worlds interpretation, you have the two mutually exclusive states, but they're not in the same universe.
Right.
Okay.
Right.
And is that
right.
the reason that, for example, I know you're a proponent, you like the idea of the Everett interpretation. Is this why you find it?
I don't particularly like the idea of the Everett interpretation. I think it's the best interpretation of standard quantum mechanics.
Okay. And so what is your objection then? Just conceptually, I mean, I know what my objection is. What is your objection to the idea that you could have a superposition of particles? Do you think that that is conceptually incoherent?
No, not at all. No, I think the quantum state propagating at the level of microscopic systems where one has a superposition of states, I don't find anything intellectually challenging.
Even of particles?
Well, the issue is, how do such superpositions ever get to deliver discrete events that are well localized in space? And that has to be explained, that has to be accounted for. And so it is on the many worlds interpretation. But that at the microscopic level there are superpositions of processes, each one of which involves something well localized, that seems fine to me. A superposition of two processes, each of which is well localized, is obviously not itself a well localized process. But it's somehow spread out in space.
But the process is not the particle. The thing that gets me is
there's no particle in addition to the quantum state. There is only the quantum state.
I see. So that is okay. Oh, this is a perfect segue. Because what I want to start talking about is some more base concepts here. One of them has to do with the nature of observation independent reality, which is kind of this common sense notion.
Sure.
And I think what proponents of the Copenhagen interpretation, and certainly the proponents of a lot of the wild interpretations of quantum physics say, is that reality is something that is non-existent until it's been observed.
Sure.
But what they mean by observation isn't interaction with other macroscopic systems. They mean conscious observation.
Right.
Now, is there any evidence that suggests it's conscious observation that determines reality? Or another way of putting it, in the phraseology that a lot of people talk about, is the collapse of the wave function, like we were talking about earlier. Sure. You have the measurement in, when we're talking about the double slit experiment, you have the measurement, which when you actually measure which slit the particle goes through, the wave function collapses, meaning we have no interference pattern. And so they say, observation collapses the wave function. What do you...
Yeah, right. Well, no, I don't think there's evidence for any involvement of consciousness, but it's understandable why people might be led to that point of view. Okay. I mean, the measurement problem is precisely the problem that if you just provide a physical description of a measurement device and put that into the formalism along with the system that is being measured, apply the unitary dynamics, what you get out is this superposition. And now at the macroscopic level, you get the superposition. I can stick in an armchair, I can stick in the walls of the laboratory, I'll get a superposition. When is there ever a problem with when does the buck stop? What breaks this endless superposition of outcome? And for many, the answer seems to be when a conscious observer actually looks.
Now, is there any evidence for that?
No, there's no evidence for it. It may be that certain people, anyway, are prepared to tolerate a superposition of macroscopic outcomes, are prepared to tolerate a superposition of a cat alive and a cat dead. What they balk at is the idea of a superposition of a conscious observer being in a superposition of two outcomes. And I think what drives this is the view that ultimately what is the given in observation is what's given in sensory stimulus. And what has to take place in order to break the superposition, it's got to happen at least when it comes to what is my sensory stimulus or what is my conscious awareness. Now, the obvious answer is to say the macroscopic superposition is broken long before it gets to my conscious awareness. It's already broken at the level of the cat being alive, the cat being dead. It's already broken at the level of an experimental device recording one output rather than another. So, the idea that consciousness comes into the picture is better phrased as we'd better make sense or get rid of macroscopic superpositions before we get to a conscious observer being involved.
So what people give examples like this. They say, going back to Schrodinger's cat example. So the cat is in a macroscopic state of alive and dead, and then when we look, then pops into one or the other.
Well, it had better pop into one or the other up to the point where we look. The point where we look is, as it were, the last resort. If you can't find a way to block it before when we look, then it must be the very act of looking that does it.
Which is precisely why they say. So I want to make that very clear, because for me, in terms of like coming from a position of, I'm very sympathetic to common sense. The idea, tell me if this is a correct analogy. So let's say that I was flipping a coin, and 50% of the time I get heads, 50% of the time I get tails. And I can't know beforehand, because I have some inherent limitation, I can't know whether or not it's going to be heads or tails. But I have a probability function. I say 50%, 50%. It would be as if it appears. What I'm saying is, when I flip the coin is in a state of heads and tails, but when I look, boom, it pops into one state. Is that a fair analogy? Right. Now, that seems to me, if it's not outrageous to say, that seems absurd.
Right. Yeah. Well, I think seeming absurd isn't a great
counter-argument
method, really, in debating these things. Sure, it may well seem absurd.
But that's a fair way. That is a fair.
It's a fair characterization of what's going. The flipped coin is in a superposition of being spin up, spin down, whatever the word superposition means. It's somehow maybe not interpretable in ordinary terms. But when I open my eyes and I look, boom, then I must see either the coin head or the coin tail. That must happen. And you spoke of what is the evidence. I mean, of course, the evidence of our eyes tells us that macroscopic things are never in strange superpositions. We don't even know what it would be like to be witnessing a strange superposition. Would it be like double vision or something? Would it be that everything is sort of made out of jelly, or I don't know what? So you speak of evidence. Well, certainly we have evidence that at the level of things we can see, we always see macroscopic objects well localized in the way that classical physics and common sense tells us. Things are well localized with well-defined properties, right? But I think the right way to understand this appeal to consciousness is that we've got to resolve the difficulty by the time we get to consciousness. Yes. Maybe at consciousness. But I think a more
that's a very good
level-headed answer is no. We deal with it already at the level of macroscopic systems. They don't have to be conscious. It's irrelevant whether or not they are conscious. And that's what happens in all three of the solutions that I've just quickly summarized. In the pilot wave theory, you never get peculiar superpositions of things built up out of particles, because these particles are not themselves in superpositions. It's just the quantum state that is. We never see the quantum state, we just see the particles. In the dynamical collapse theory, the quantum state becomes well localized when you've got interactions with other particles. You might ask, well, what are the particles doing here in relation to the state? That's quite a subtle question. But anyway, bottom line, the fundamental thing is the quantum state, and the quantum state becomes well localized when you get to anything that could count as a macroscopic system. Okay, and then back to many worlds, you get these macroscopic superpositions, all right, but all macroscopic objects are caught up in each term of the superposition, so that if you only look at, ultimately you get a superposition of different universes, but each universe, so described, macroscopic bodies are well localized, and so forth. In none of these three approaches do you ever need to make any reference to consciousness.
Excellent. And so I'm going to give one more example. and then a point, and then another question. So would it be fair to say, returning to the coin flip analogy, what the many worlds interpretation says is that when you flip the coin, or when you look, I should say, it's not the case that there was ever a actual superposition in the same universe. You have one universe in which it's heads, and you have another universe in which it's tails.
Right.
Okay.
Right.
So then here's the point. Is it fair to say that the great deal of words that have been written about the collapse of the wave function as it relates to consciousness are most likely unjustified when some of the conclusions come from people because they take this and they say this is the spiritual nature of consciousness, that consciousness is this divine thing which in a very real way creates reality. You don't buy that?
No, and I don't think there's any evidence coming from quantum mechanics to that effect.
Okay, so then I have a few more questions for you, a few more concepts to get through. So let's talk about a central concept or a central formula in quantum mechanics, and that's Bell's theorems. Can you just kind of conceptually explain what is Bell's theorems? What does it try to do?
Sure. What Bell's theorem is a very simple model as to what sorts of correlations can be produced by spatially distant systems. And there's a locality assumption, one or two other apparently very innocuous assumptions, which then lead one to conclude that the various correlations that can be produced are constrained by an inequality. Okay, we don't have to go into the mathematical details. Right, so quantum mechanics, you can actually do these experiments producing correlations in these spatially remote systems, and you find they violate this inequality. Mm-hmm. So the straightforward implication seems to be that the locality assumption, together with let's not question the one or two innocuous assumptions, let's look at the locality assumption. Okay. That locality assumption is violated in quantum mechanics. So that is what is taken to be the import of the Bell inequality, or violation of the Bell's inequality. The quantum mechanics is non-local in some fundamental respect.
So what does that mean?
So the locality principle that appears to be violated by quantum mechanics appears to be something like this, that by performing a measurement in some remote place, that the outcome of that experiment in that remote place cannot affect what goes on locally, nearby. Right. If those two places are sufficiently remote from one another, we're talking about they're sufficiently close to the same time, such that it would need faster than light influence. That is what we mean by locality. But this locality assumption seems to be violated. Actually, it's explicitly violated in the pilot wave theory. Right. It's pretty explicitly violated in dynamical collapse theory. The situation with many worlds theory is not so clear.
Okay.
There's fairly compelling arguments to say that actually no, there's no violation of locality according to the many worlds interpretation.
Okay. Is it fair? Could I phrase it this way, that what Bell's inequality is supposed to show is that there is no local hidden variable.
Sure.
So if it's the case that there is a hidden variable, it must be the case that it is a non-local hidden variable. Right.
Yeah, initially Bell's result was tied to hidden variable theories. Mm-hmm. It was investigated by Bell in the context of hidden variable theory. He was interested in the question of, what he saw was that the pilot wave theory was non-local. He was interested in the question, would any hidden variable theory that reproduces the results of quantum mechanics be non-local? And the answer appeared to be yes.
Now, isn't that evidence for something like pilot wave theory? It seems like that would be the intuitive conclusion. Well, if it's the case we don't even hold on to locality, then why would we posit that there's this pilot wave phenomena going on?
Well, that would seem to, for many, that was taken as evidence against hidden variable theory. It was mostly understood from the late 60s on that Bell's theorem was all about hidden variable theories. Mm-hmm. And what it said is a hidden variable theory that reproduces the results of quantum mechanics must be non-local. That was taken by most, to mean...
It's unacceptable, in other words.
Hidden variable theories are unacceptable.
I see. So what I'm saying is, now, Right, that's very interesting. What I'm saying is quite the opposite. So that's almost like that's supposed to disprove the idea of hidden variables, but if we just change the assumption of locality, then it seems like, in fact, that's not the case.
That you could have non-local hidden variable theories.
Sure.
Sure, of which pilot wave is an example.
Right.
So, I mean, okay, I think this is perhaps what you're getting at. You might have thought pilot wave theory, okay, that's great, but unfortunately got no locality in it.
Mm-hmm.
Let's find a better hidden variable theory that is local. Bell's theorem tells us, or violation of Bell's inequality tells us we can't construct such a theory, therefore let's just make do with pilot wave theory.
Well, kind of the way that I'm coming at it is I'm not a big fan of the many worlds interpretation or the Copenhagen interpretation, and because I'm not a physicist, I have yet to see the dire implications of giving up locality. Now, I realize general relativity is based on this idea of locality. Can we talk just a little bit about that idea of why locality is such a central concept and why it would be a huge deal if it's the case that non-locality is
right? So it
true.
Depends very much on the kind of non-locality.
Okay.
One kind of non-locality that involved faster than light signaling would directly violate special relativity and general relativity. So if we had evidence of that, we'd have a radical falsification of one of the two or three fundamental theories of modern physics.
Mm-hmm.
Right. So that's a certain sort of non-locality. This is the kind of non-locality that would involve faster than light signaling.
Okay.
Okay, now the violation of locality that goes on with Bell's inequality, violation of Bell's inequality, does not imply faster than light signaling.
Oh.
So the kind of non-locality that a hidden variable theorist would say we have to accept is, when it comes to actual experiments that you can perform, not in contradiction to either special or general relativity.
Interesting.
Because
Okay.
it's not the sort of non-locality that you can use to signal with.
So to me, just again intuitively, that seems like further reason to believe that the pilot wave theory is the one which doesn't have any unintuitive conclusions, doesn't necessarily violate principles of special relativity. So why, like in your mind, for example,
right. Why not embrace it?
Yeah, why not?
Sure,
Yeah.
absolutely.
Yeah.
Answer, because there's two answers. I mean, they can be taken together or they can be taken singly. So one problem is we don't have a relativistic pilot wave theory, or not one that describes any non-trivial relativistic phenomenon. So the most trivial, but the most simple of relativistic phenomena in quantum theory is, say, particle creation or annihilation. We don't have a pilot wave theory that can describe particle creation or annihilation. You can try to concoct a sort of hybrid of pilot wave theory with dynamical collapse theory. People have produced some toy models, but those toy models don't connect with actual physics, and the prospects seem poor. What you can try to do, and what pilot wave theorists have tried to do, is typically work with field configurations rather than with particles. So the fundamental reality is built up from fields, and you can have a sort of the hidden variable theories in terms of this dynamically evolving field. There isn't really a particle interpretation alongside of it, and I mean, perhaps the bottom line is also to say the dynamical evolution of these fields is not relativistically invariant.
Now, is that in terms of it can't be, or is it just that work hasn't been produced yet?
Well, it seems that it can't be.
I see.
It really seems that you need a privileged reference frame in order to describe any evolution in terms of classical fields using pilot wave theory ideas. In other words, there really does seem to be a fundamental discord between relativity and pilot wave theory ideas. That's one sort of reason not to embrace pilot wave theory. Another reason not to embrace it is because pilot wave theory has the quantum state. It has the unitarily evolving quantum state. That unitarily evolving state involves also macroscopic structures. That unitarily evolving quantum state has all of the structure that the many worlds theory says it has. You can read out from that macroscopically evolving quantum state all of the details of all of the worlds, with all of the observers in each of the worlds seeing the various outcomes that they have. You can decipher, discern in that unitarily evolving quantum state all of the structure that there is in the many worlds interpretation. Now, a pilot wave theorist has got to say, okay, but I'm somehow discounting all of that. I'm not going to take any of that seriously.
But it doesn't imply that those different states have an actual existence, like the many worlds interpretation.
No, the quantum state is an actual quantum state, is an actually unitarily evolving quantum state, just as it is in many worlds.
Okay.
They've got everything that many worlds theory has, but they are adding in particle trajectories in the non-relativistic case.
I see.
Now, how is it that you add in additional stuff and you get out less stuff? It's
right.
kind of an interesting
I see.
puzzle there. Okay, so that's a second kind of objection to pilot wave theory. And the third kind of objection to pilot wave theory is it's just proved, it's never been fruitful, and it puts in by hand a picture of reality. You've got to discount a big major part of it, namely the many worlds, because that's in there too. But it's putting in by hand a picture of reality that is just more, sort of intuitively acceptable.
Right. Which I intuitively like.
Right. But this is bad methodology in physics.
By hand is a great way of putting it.
Right. It's a bad methodology. You might as well put in by hand a little rule that says, these incredibly weak electromagnetic excitations, electromagnetic signals that we're getting from the sky, that they're incredibly minute and tiny, and we should basically ignore them in our picture of the universe. That really the universe is...
Because it's prettier otherwise.
Yeah, that's right. It's just nicer to think that the bright lights in the sky are... just bright lights. Let's not go into, all of the details of the electromagnetic, because it's all electromagnetic pretty well. We have some cosmic rays results, but otherwise everything we know about the universe comes through electromagnetic signals. I mean, there is something that's philosophically interesting about many worlds that I think ought to be noticed, actually, especially if you're particularly more interested coming at this from, say, epistemology. The many worlds interpretation carries with it an analysis of probability which is better than anything we've ever seen before in any physical theory, in any toy model. So if you're interested in why is it that there's some objective stuff out there in the world that dictates what we ought to believe in the ways of subjective degrees of belief that credence should conform to, the Everettian quantum theory or many worlds theory explains why. It tells us why we should conform our rational expectations to certain physical quantities out there in the world.
Interesting.
Right. And no other theory does that. And it tells us what objective probability is in the world. And again, no other theory does it. Pilot wave theory doesn't do it. Dynamical collapse theory doesn't do it. They sort of build in probabilistic structure in the dynamics, in the case of collapse theory. But what you'd have to say is to the question of what is probability, you'd say, well, it's just built into laws. You want to say, what is it about a given physical situation that makes the probability 0.6 rather than 0.2? What is it about that physical situation? And the answer will be, it's just built into the laws. In pilot wave theory is something similar. In many worlds theory, you say, oh, what makes it 0.6 rather than 0.4 is because there are amplitudes for branches, the modulus squares of which are 0.6 and 0.4. These amplitudes for branches are out there in the world.
So the last question I want to ask you is we're pointing at a fundamental tension between quantum mechanics and regular macroscopic mechanics.
Sure.
Is there any way right now that these two things can be put together in a coherent way? Because what I have heard is that when you're looking at microscopic phenomena, it appears as if the laws of physics are different than when you're looking at macroscopic phenomena. But by the time you get to macroscopic phenomena, we don't really have to worry about all the weird quantum phenomena. And even if those two principles, like even if there's two actually different laws of physics that we're talking about, and they're mutually exclusive, we shouldn't worry about it because everything resolves itself.
Yeah, so it just doesn't work that way. I mean, the reason it doesn't work is that we don't have a classical physics for tables and chairs. We really don't. Classical physics was never able to explain stability of macroscopic structures. It was never able to explain how you can have a grain of dust, even, which has a stable shape. Try, apply classical physics, point-particle interactions, whatever potential functions you like, it's unstable. It's quantum mechanics uniquely that explains and predicts stability of structures, bound states. It explains why atoms are stable. It explains why collections of atoms can stably be coupled together to one another so as to have a stable shape and structure and form. And that's what's needed to build up and use actually any branch of the special sciences, metallurgy, crystallography, hydrodynamics, you name it. All of those branches of physics require stable structures, actually. They're provided always by quantum theory. So you can't do without quantum theory. There is no autonomous classical theory of matter.
So would you say it's fair to say, if to the extent that there's any tension between the two, quantum mechanics is more fundamental, and therefore if any theory needs to be adjusted, it's what lays on top of what is fundamental?
Yeah, absolutely. And what's, this wasn't obvious back in the 20s and 30s when Bohr was laying down his interpretation. What Bohr thought is that classical physics is the more fundamental, and quantum mechanics is just a calculus that explains why we have small departures from the classical at small dimensions. Okay, so what changed that picture is partly what I've already spoken about. Classical physics actually doesn't account for stability of matter at all. But partly that quantum mechanics increasingly was able to recover quasi-classical, approximately classical physics insofar as issues of... it puts in the stability, and then it shows how those stable structures evolve over time in approximately classical ways. Okay, you might think, look, this is a bit weird. Classical theory doesn't give stability, but it does. There is a way of being classical, but there isn't a classical way of being stable. That's about right. There is a way of being classical, Newtonian mechanics. We all studied it at school a little bit. There's a way of being classical, but what it is that behaves in that approximately classical way can't be accounted for in classical principles. Quantum mechanics can account for what it is that, not only for what it is that obeys those approximately classical equations, but that thing obeys those approximately classical. We can deduce that, extract that from quantum physics itself. The way of doing that, though, is exactly the way that yields the many worlds interpretation. It's not a route that makes much sense either from dynamical collapse or from pilot wave theory. Pilot wave theory, the methods used to get out stable structures evolving in approximately classical ways seem to be a whole sort of dimension of physics that in principle shouldn't be there at all, because what pilot wave theory is telling you is you've got these classical trajectories. Well, the trajectories may not look particularly classical, but they're trajectories. You build in what seems to be required for classicality right there in the macroscopic level. And then you ask, so how come we see at the macroscopic level anything classical? And in a way, the pilot wave theory wants to say, well, look, it's just more of this stuff. So, there is no complicated story. It's just more and more trajectories. But actually what you've got to do is you've got to show how the more and more trajectories actually start to behave as stable bits of matter, obeying approximately classical equations. And the only way to do that is not through the guidance equation. The way to do it is the same way that it works in many worlds theory. So this is another, you understand, you get lots of hints that pilot wave theory doesn't actually deliver, or insofar as it delivers, it's giving you a very simple intuition for things like the two-slit experiment, but not much more. Right.
I think that's an excellent note to end on.
Okay.
I really appreciate this conversation.
Okay, well, thank you.
So that was my interview with Dr. Simon Saunders of Oxford University. I hope that you found it helpful. Obviously, the topic is gigantic. There's lots and lots to say. There's lots and lots that has been said, much of which in my evaluation is nonsensical, and it stems from a lack of understanding the basics. So if you're new to the realm of quantum mechanics, I hope that this interview can serve as a springboard to learn more information about the competing theories in the world of quantum physics and the different experiments that are taking place, because it's really obviously a fascinating and cutting-edge area of inquiry. I've also done a little bit of writing on the topic specifically combating the explicit irrationalism that comes from people drawing from quantum mechanics to try to justify conclusions like, we can't know anything about the world because reality is logically contradictory, and the universe is just a great big blurry paradox that only resolves itself into one way or another by our minds, which are at the center of everything. I combat these ideas very sharply, directly, and perhaps derogatorily in a piece that's called Quantum Physics and the Abuse of Reason, which is one of the most popular articles that I've written. If you just Google that title, it'll come up. But I'm very glad that I got Dr. Saunders to sit down and work through these things with me. I also learned a lot myself. So this interview took quite a while to put together, as you can imagine. And if you valued it, if I've created value for you, then please go to patreon.com/Steve Patterson and show your support. If you want more interviews and content that's produced like this, you can become a patron of my work, which means that you pledge $1 when I release new material like this. I am trying my best to create as clear and rational a worldview as possible. All right, so I have lots more to say on the topic. I'm sure I'll do more interviews and more detailed breakdowns of these ideas. And in fact, coming up, I'm going to do a whole breakdown episode where I'm going to spend a lot of time on this interview to give you more of my own personal beliefs and more further clarification of the ideas that we've been talking about. So thanks for listening, everybody. I really hope you found this useful, and have a great day. Observe with the double slit experiment. So in this example, when I'm talking with the professor, we're talking about light, because that's the actual setup that physicists use when they're performing the double slit experiment. But conceptually, you can also think of it another, perhaps even more intuitive way. Instead of light, let's talk about sand. So imagine you have a setup of 3 parts. On the top, you have a hopper that's full of sand. And the sand is slowly dripping down onto the second part of the experiment, which is, let's call it a card. On the card, there are 2 slits in the card that allow the sand to pass through those slits. Below the card, we have a screen where we can see the resulting pattern that happens once the sand goes from the hopper through the slits down onto the ground. So sometimes we can plug one of the slits to record what happens as the sand passes through the one slit. We can have both the slits open and record the pattern that happens. So conceptually, that's what the double slit experiment is. You have 3 parts. You have the reservoir of particles that are being shot at a card, or I call it a plate with 2 slits in it, and then you have the screen behind it to record the pattern that results as those particles go through the slits. And in that plate that we're shining the light at, we have, let's just say, 1 slit. Now, if we do that and we shine the light at the plate and see what happens, if we're seeing what happens to the pattern on the wall. Saunders. So first of all, thank you very much for talking with me today.
It's a pleasure.
I have asked a great deal of you because, as you know, in the world of philosophy and the general public, quantum physics gets thrown about all the time. People try to justify all kinds of remarkable propositions when they're talking about quantum physics.
Indeed.
What I've asked is if we could slowly work through the basic concepts, so when people are trying to evaluate the plausibility of some of these ideas, they'll have kind of the conceptual toolbox that they need.
Right.
So correct me if I'm wrong at any point in this, that one of the peculiarities in the world of quantum physics, kind of the first experiment or the foundational experiment, is called the double slit experiment. That's kind of where we see this remarkable phenomena that people make all kinds of incredible claims. You can analyze quantum physics by analyzing the double slit experiment. And what that is we have three parts in our experiment. We have a light source, we have like a plate that we're going to be shining the light at, and then we have a screen. Okay, so this is the first time I want to jump in because when talking about quantum mechanics, you must understand fully the setup of the double slit experiment. Really, the double slit experiment is central. That's really the whole, everything really follows from the phenomena that you can observe conclusions. They try to say, oh, reality is logically contradictory, we can't know anything about anything, and the universe is a great blurry paradox, or consciousness is at the center of the entire universe. These ideas, I think, are foundationally inaccurate, dangerous, and are about as far away from rational, clear-headed thinking as possible. And quantum physics is arguably the area that gets the most citations from the irrationalists. An extraordinary amount of words have been written drawing from the supposed conclusions of quantum physics to show how irrational the world actually is. But in my own research, when I actually dove into the field, I found a lot of these conclusions to be mistaken. I think people who draw from quantum physics to make radical conclusions don't actually understand what they're talking about. They make grave errors with very big implications. So what I did explicitly while in England was set up an interview at the University of Oxford with a professor of the philosophy of physics to try to get down and pin down the core concepts in quantum physics for everybody to understand. And this interview is with Dr. Simon Saunders, who is indeed this professor I was looking for. Dr. Saunders is a professor of the philosophy of physics at Oxford University. He's written a ton of papers on the topic, he's written a few books, and what I find of inestimable value is that Dr. Saunders focuses on concepts. Very often when you have elite
quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Hello, everybody, and welcome to episode number 14 of Patterson in Pursuit. It seems like these interviews just keep getting better and better and more exciting. This interview I am the most excited about because, in my own intellectual pursuit, I have come across several areas of thought that people draw from when they try to make what I call irrational intellectuals who are nose deep in their own research. They get mired up in a lot of jargon, a lot of mathematics, a lot of specifics that nobody outside their own field understands. And in this interview, we only talk about mathematics really in the abstract. We just focus on the concepts, which I think is necessary if you want to clearly understand whatever field you're talking about. You have to be able to understand it clear enough where you can break down the basic concepts. That's not to say, however, that this is an easy interview or this is something that you'll be able to sit down and, halfway ignore and still be able to follow along, especially if you have no background in physics whatsoever. So what I've done to help make it a bit easier is for about the first 15 minutes or so, I'm going to be chiming in to give additional clarity to the interview as it's taking place. So maybe 5 or so times, I'm going to jump in and try to break things down to have that much more clarity. So before I start this interview, I want to give a gigantic shout out to all of my Patreon supporters, especially the ones who support my work the most. Thank you very much, Mark Gouvet, Charlie Davis, Melvin Martinez, Sean Baleda, John LeBlanc, the Georgia Freeman, Michael Sedlak, David Richardson, Samuel Robert, and David Baumberger. Thank you all very much for supporting the creation of a rational worldview, and everybody else that is supporting at smaller levels. Your support makes these interviews possible. All right, that's enough for me. I hope you really enjoy my interview with Dr. Simon